Often we will need to analyze circuits that have more than one capacitor in them. Multiple capacitors are often used because capacitors aren't made for every possible desired capacitance out there. Sometimes you may need to use multiple capacitors to achieve a desired capacitance. There are two basic ways in which capacitors can be combined. The first is in parallel. You know something is in parallel if an electron traveling around the circuit has to make a choice of which capacitor to go to. So this picture here shows two capacitors that are wired in parallel with each other, and then this parallel connection is connected to a battery. So an electron coming from the battery would have to choose whether to go to this capacitor or to this one. Another way of seeing this is you look for junctions. Junctions are places where two or more wires come together. So here you can see there is a junction, here there is a junction. So a current flowing around this circuit would have to split at this junction. It would have each electron making the choice to go one way or another. So if you have two capacitors that are on branches, so a branch goes from a junction to a junction, or here from a junction to a junction. So if you have multiple branches that share junctions, then those capacitors on those branches are in parallel. Now, the important thing about parallel, regardless of the kind of component you have on branches that are parallel, is that the voltage drop is the same for each branch. And so it's the same across capacitors. So batteries act a bit like voltage pumps. So remember before we were talking about voltage as a height, and the higher the voltage for positive charges, the higher the height. So one way of thinking of circuits is that a battery is like a pump. It raises the current up to a higher potential. So it raises the potential, and then capacitors are like waterfalls where the potential falls back down. So if you have some charge going around this circuit, the charge is raised by the pump, the voltage is raised by the pump, and then it falls as it goes over a capacitor. So by the time electrons come back to the battery, they need to be back down at the level where the battery can pump them up again. So regardless of which capacitor the electrons went to, regardless of which branch we're talking about, the size of the capacitor waterfall needs to be the same. There needs to be the same voltage difference across the one branch as the other. So it's like having parallel waterfalls. If these are the two capacitors, then the voltage drop, the height drop across both of them must be the same if they are in parallel. So here's another configuration where we have two capacitors in parallel, and we can tell because we have two branches, two places, directions that the current could go. An electron has to make a choice whether to go this way or to go this way. And so these two capacitors are in parallel, and they would have the same voltage drop across both of them. So we can use this knowledge to combine capacitors. If we want to replace parallel capacitors and know what is the equivalent capacitance, if I were to replace these two with just a single capacitor, what capacitance would that single capacitor have to have? I could also have a bunch of different capacitors, and these are all in parallel. And if I were to replace those with a single equivalent capacitor, what would that value of that capacitor need to be? So one thing that we know is that the equivalent capacitance or the equivalent capacitor needs to have the same charge on it, or it needs to store the same amount of charge that is stored in the two capacitors combined. So we can say that Q1 plus Q2, the charge stored on capacitor 1 plus the charge stored on capacitor 2, needs to be stored on the equivalent capacitor, because for the equivalent capacitor to store the same amount of charge or energy, it has to be equal to the sum of the charges stored on the individual capacitors. So we also know by rearranging the capacitance equation that the charge stored on capacitor 1 is equal to capacitor 1's capacitance times the potential difference. And the potential difference is the same for both capacitors since they are in parallel. So we can rewrite this charge expression and say that the equivalent charge on the single capacitor is equal to the charge stored on capacitor 1, which we write like this, and the charge stored on capacitor 2, which we write like this. And so that is then going to be equal to the equivalent capacitor times the potential difference. The potential difference across this equivalent capacitor would be the same as the potential difference across either of the two capacitors. The waterfall needs to have the same height as either of these two. So then we notice the potential difference is the same in all of these terms. We can divide all of the terms by potential difference, and we find that the equivalent capacitor is equal to the sum of the capacitances of the two individual capacitors. So if we have similarly a whole bunch of capacitors in parallel, we can just add the capacitances to find the capacitance of an equivalent single capacitor. So that's pretty easy. If you have capacitors in parallel, just add up their capacitances, and that is the capacitance that the whole set has if you were to replace them with a single equivalent capacitor. There is another arrangement of capacitors that's possible, and that is in series. So for capacitors in series, if you had an electron traveling around the circuit, now of course you can't have a single electron travel completely around the circuit, it would basically come to this plate, get stuck, and then an electron from this plate would go around and then go to the second capacitor, and then an electron from this plate would head back to the battery. But regardless of that, if you have capacitors in series and you had electrons traveling around the circuit, one would have to go through both capacitors to get back to the battery. So you have one capacitor after the other. Now, if you have capacitors in series, we know that the same charge has to build up on each set of capacitor plates. The reason being that if you have an electron travel from the battery and hit this capacitor plate, it will cause one electron to move from this plate to this plate, and then one electron to move from this plate to this plate, or back to the battery. So the same number of electrons added to this plate as subtracted from this one, as added to this plate as subtracted from this one. So each capacitor gets the same charge built up on its plates. Another thing we know is that if we look at this picture, here we have some waterfalls that are in series, one right after the other. And we can see that the sum of the voltage drops across the capacitor would have to be equal to the voltage that you gain from the battery. So if we want to replace some series capacitors with a single equivalent capacitor, we know that this equivalent capacitor would have to have a voltage drop equal to the sum of the voltage drops across the two equivalent capacitors, and the sum of the voltage drops would be equal to the battery that they are attached to. So for these voltage drops, we can rearrange the capacitance equation and find that the voltage drop is equal to Q, the charge on each capacitor, divided by its capacitance. So that means that the charge on the equivalent capacitor divided by its equivalent capacitance would be equal to the charge over the first capacitor's capacitance and the charge over the second capacitor's capacitance. So the equivalent capacitor gets the same amount of charge as both of these two, because if it's acting in an equivalent manner, then the same number of electrons will be added to one plate and subtracted from the other as each of these two individual capacitors. So since the charges are all the same, we can divide through by charge and those cancel, and we find that 1 over the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. So for series capacitors, if you're adding capacitors in series, you need to take 1 over the capacitances, add them up, and then take 1 over that answer in order to find the equivalent capacitance. So let's look at an example problem where we can do this. So in this example problem, we have two capacitors. They have capacitances of 1 microfarad and 0.5 microfarad, and they are connected in series. The system is connected to a 100-volt battery, and we want to know what charge accumulates on the 1 microfarad capacitor. So to solve this problem, let's first redraw our circuit diagram showing and labeling the capacitors and the voltage of the battery. So I have in this problem two capacitors that are in series. The first has a capacitance of 1 microfarad, and then the second one has a capacitance of 0.5 microfarads. And I could have switched the ordering, it doesn't matter. And then these two capacitors are hooked up to a battery, and the battery has a voltage of 100 volts. So I need to find what charge accumulates on these capacitors. So I know I have my capacitance equation. C is Q over delta V. And I know that overall there will be a 100 voltage drop over both of these capacitors put together. So if I gain 100 volts from the battery, I have to lose it over the two capacitors. But I'm not sure yet how that's kind of split up. So for an individual capacitor, I have the capacitance, but I don't know how the voltage is being divvied up between the two capacitors yet. And so it's hard for me to find the charge yet. So what I need to do is to find an equivalent, simpler circuit where there's just one capacitor, because that will allow me to find the charge on that single capacitor, which would be equivalent to these two. So what I need to do is add these two capacitors together and find a simpler circuit where there is just one single capacitor that is equivalent to these two, and that's hooked up to the 100 volt battery. So I need to add these two capacitors together. So the two capacitors are in parallel, which means I need to add reciprocals. So 1 over the equivalent capacitance is going to be equal to 1 over the first capacitance, which is 1 microfarad, plus the second capacitor, which is 0.5 microfarads, and 0.5 is equivalent to a half. So this is 1/2, and I'm writing it as a reciprocal, 1/2 of a microfarad. So if I add 1 microfarad plus 1 over 1/2, which is the same as 2, then I get a total of 3 over 1 microfarad. So I'm just adding these fractions together. So then the equivalent capacitance, to find that, I take 1 over this answer here. So 1 over that is 1 microfarad over 3, or 1/3 of a microfarad. So then I know that this capacitor has a capacitance of 0.333 on forever microfarads. So it's 1/3 of a microfarad for my equivalent capacitor. So now I can find the charge that would build up on this equivalent capacitor, because I know its capacitance, and I know that the battery, if I'm gaining 100 volts from the battery, I have to lose 100 volts over this capacitor. So I know the potential difference across the capacitor. So if I rearrange this equation to find charge, Q is equal to C delta V, and I have 1/3 or 0.333 microfarads, so that's times 10 to the minus 6 farads, and then the potential difference across this capacitor would be 100 volts. So that gives me, that's going to be equal to, it'll move the decimal point 2 places, so that's 33.3 times 10 to the minus 6 coulombs. And then moving that into using some of the unit prefixes, 33.3 times 10 to the minus 6 is equivalent to 33.3 microcoulombs. So there's 33.3 microcoulombs on this equivalent capacitor, 33.3 microcoulombs. So one thing I know about series capacitors is that if I know the charge on an equivalent capacitor, that same charge is on either of these two capacitors. Because this 33.3 microcoulombs represents a certain number of electrons that were added to the one plate and subtracted from the other by the battery. So in doing the same thing with this equivalent circuit, the battery would add the same number of electrons to this plate, subtract them off of this one, add them to this one, subtract them off of this one. So each of these two capacitors also gains 33.3 microcoulombs worth of charge on their plates, one of them being positive and one of them being negative. So that means that if I want to know the charge that accumulates on the 1 microfarad capacitor, then that is going to be 33.3 microcoulombs. Now we may come across circuits that have bits that are in parallel and bits that are in series. So you can have a very complex circuit with a bunch of different capacitors that you need to add together to find an equivalent circuit. So the tips for combining capacitors for more complex circuits is, first off, you want to identify the branches of the circuit. You want to find the junctions where the electrons would have to make a choice, where you have multiple wires branching off or coming together. You want to figure out where those junction points are, and then branches go from junction point to junction point. Find the branches of the circuit. Look to see if there are any capacitors, if there are multiple capacitors along a single branch. And if there are, then you would add those capacitors in series and replace it with a single equivalent capacitor. And you do that for each of the branches. Next, now that the branches all just have a single capacitor, you look to see if branches share junctions and replace those those branches that share junctions, add them together in parallel, add those capacitors in parallel, and replace those with a single equivalent capacitor. And then you go back and repeat steps 1 through 3 until you just have one capacitor remaining in your circuit. So here is a circuit that's a little bit more complex than the last one we looked at. And C in this circuit, which is labeling some of these capacitors, is equal to 36 microfarads. We want to determine the capacitance for this entire combination of capacitors. And you can imagine where you see the black circles that there are connections running from those black circles potentially to some battery. So let us first reproduce this circuit. So in this circuit we have a capacitor here with a capacitance of C. We have a capacitor here with a capacitance of 2C, and then we have another capacitor here with a capacitance of 2C, and then we finally have a section here that has a capacitance of C, and then we have this other point that, and there may be a battery hooked up between these two parts of the circuit. All right, so if we go back to our steps for combining capacitors, we see that the first thing we need to do is identify the branches of this circuit. So we want to find the places where electrons might have to make a choice, where multiple wires are coming together. And I see here that I have two junction points in my circuit, there and there. Those are the junctions in the circuit. So the branches then go from junction to junction. So that means I have multiple branches in the circuit. So, and you could probably count these as junctions 2. There might be some more circuit over here. But you go from junction point to junction point and look to see if there are multiple capacitors along each branch. So here's one branch in my circuit. Here is another branch in the circuit. And branches go from junction to junction. So then I look to see, are there multiple capacitors along any of the branches in my circuit? So this branch has just one capacitor. We count this as a branch, it only has one capacitor. But here we have two capacitors that are along a single branch that goes from a junction point to a junction point. So we have two capacitors along this branch, and so we need to add those in series, because if you're going along this branch, you encounter one capacitor, then the other. So these are in series. So if I'm to find an equivalent capacitor to these two, 1 over that equivalent capacitor is going to be equal to 1 over 2C plus 1 over 2C. Now if I factor out a 1 over C, this is going to be equivalent to 1 over 2 plus 1 over 2, or a half plus a half, which is just equal to 1, so this is 1 over C. So 1 over C equivalent is equal to 1 over C, meaning that my equivalent capacitor is equal to C. So I can replace these two capacitors with a single capacitor of capacitance C, and I get an equivalent circuit. So let's draw that. So now my circuit looks something like this, or a circuit segment. I have a capacitor here of C. I have a capacitor here of C. And then on this branch, I just have a single capacitor. I can draw it anywhere along the branch. I'll just draw it here. It's nice and symmetric. So this is also C. All right, so then the next step is to add branches that share junctions in parallel. So I have a junction here and a junction here, same as before. And I want to see, do I have branches that share that pair of junctions? And yes, I have this branch and this branch that share this pair of junctions. So I can then add these capacitors in parallel and replace this arrangement of capacitors with a single equivalent capacitor. So if I'm adding these two capacitors in parallel, I just add the capacitances. So the equivalent capacitance would be equal to C plus C, and that's going to be equal to 2C. So then I can simplify my circuit further. I have this capacitor here, and it has a capacitance of C. And then this two capacitor arrangement, so this whole series of branches can be replaced with a single capacitor, which has a capacitance of 2C. All right, so now I've eliminated these two branches, replaced it with a single one, and my equivalent capacitance is 2C. So then I go back and repeat steps 1 through 3. Identify the branches of the circuit. Well, I really only have one branch now. There's no places where electrons can make a choice and go one way or the other. So I just have one branch. Add the capacitors along this branch in series. Okay, so this capacitor is now in series with this one. They're one right after the other, so I have to add them in series. So 1 over C equivalent is going to be equal to 1 over C plus 1 over 2C. If I factor out a 1 over C, then that's equivalent to 1 plus 1 half. So 1 plus a half, 1 over C, 1 plus a half is equal to 3 halves. And then this is 1 over C equivalent. So my C equivalent would be the inverse of this, which is 2C over 3. So 2/3 C. So I can replace both of these with a single equivalent capacitor that has a capacitance of 2/3 C. And so that is the one capacitor that remains in my circuit. All right, so if we want to know then a number for this equivalent capacitance, because we know that C is 36 microfarads, then we can take and put 2 times 36 microfarads and divide it by 3. So 2/3 of 36 microfarads, that's going to be equivalent to 24 microfarads. So 24 microfarads is the equivalent capacitance for this circuit combination that is, or from the capacitor combination that is shown for this entire circuit segment. So next let's look at this question. Let's suppose you have a 20 microfarad capacitor and a 10 microfarad capacitor. How should you wire them to maximize the effective capacitance of your circuit? In parallel, in series, or would both arrangements give you the same value?